Okay. So let's start. I was trying to write down everything that we had proved last time because we were in the middle of a proof. I didn't quite finish it, but I'll remind you where we were. So we were proving this theorem by Weinstein, which says the following: if you have an n-dimensional compact Riemannian manifold, so compact, of course, is complete, but even better, it's oriented, so it's orientable, and we've chosen an orientation, and positive sectional curvature. And then if you have an isometry of this Riemannian manifold, which either preserves orientation in the even dimensional case or reverses orientation in the odd dimensional case, then this isometry has a fixed point. Okay? There's a point which is sent to itself by F. And so we started the proof last time, and we said, well, suppose for the sake of a contradiction, suppose there was no fixed point. Then, well, this function that takes a point Q and sends it to the distance from Q to F of Q is a continuous function. M is compact, so it attains a global minimum. And if there's no fixed points, that global minimum is positive. Okay, and then we said we have these 2 points, P and F of P, they're not the same. There exists a length minimizing normalized geodesic joining them. There might be more than one, but there's at least one. That's using the completeness. And what we did is we showed, using this condition about the orientation preserving and even dimensional and reversing in the odd dimensional, that there exists a vector, unit vector, E1 in TPM orthogonal to gamma prime of 0, such that if E1 of T is the parallel transport of E1 along gamma from P to gamma of T, then I'm gonna skip this. I'm gonna come back to the picture. Then if beta is the geodesic with beta of 0 is P and beta prime of 0 is E1 at 0, then F compose beta is the geodesic with F compose beta at 0 is F of P, and F compose beta prime at 0 is E1 at L. That was the big deal, right? So here's gamma prime at 0, gamma prime at L. This point is F of P. We were able to find some vector E1, which is orthogonal to gamma prime, so that when we parallel translate it, this is E1 at L, this is E1 at 0, and the geodesic beta passes through P with initial velocity E1, and the geodesic F compose beta, we know F compose beta is a geodesic because F is an isometry. And of course, at time 0, it passes through the point F of P because beta passes through the point P. What was not clear is that we can arrange so that the initial velocity, this is an F, the initial velocity of F compose beta is the parallel transport along gamma of the initial velocity of beta. That's where we used this condition about F being orientation preserving in the even dimensional case and reversing in the odd dimensional case. We had this linear algebra lemma. I'm not going to repeat all that because we're not going to use it again. We just need to start from here. Yes. Sorry, yeah, this picture is bad. Yes. gamma prime of L. This is E1 of L, and what color is it? Green. F composed beta. Thank you. Okay, so we were at this point. What we haven't used yet is the positive sectional curvature assumption. We've used everything else. Okay, now we can start from here. I guess I have to erase this. So we're looking for a contradiction, and that will complete the proof. And we're going to use the second variation formula again. So let's let sigma be the variation of gamma given by sigma of ST is X gamma T S E1 of T with variation vector field E1, okay, E1 of T. So note this epsilon here, I might have had to shrink it from this, right? There's this geodesic is defined for some time epsilon, so is this one. I can take the minimum. But remember, when we have a vector field along gamma, there's some by the compactness of the image of gamma, there's some epsilon I can take to basically exponentiate that vector field to get a variation, right? And so I might have shrunk that epsilon might be smaller than this one, but I can find some positive epsilon that works. Notice that this vector field doesn't vanish. This doesn't vanish at the endpoints. So this is not a proper variation. Nevertheless, those two extra terms in the second variation formula, which always vanish for a proper variation, are still going to vanish here, and you'll see why in a second. So recall we had E double prime of 0. So let's let E be the energy of this variation. The second variation formula said that this is going to be 0 to L V prime minus R of V gamma prime inner product V dt, that was the integral term, plus ds of d sigma ds gamma prime at 0, 0, 0a, 0l, minus ds of d sigma ds gamma prime at 0, 0. This is what I was calling V2 alternate 2 lectures ago, last Wednesday. Okay, so let's see what happens here. V of t, which is E1 of t, is parallel. That's the way we constructed it. We took E1 at TPM and we parallel transported it. So this says that V prime is 0. So this first term is gone. Also, what is sigma of S0? If we look at the formula for sigma, it's X gamma T, X gamma 0 of S E1 0, which is exactly beta of S, right? And S sigma of SL is X gamma of L S E1 of L, and that's F composed beta of S, right? Because of this fact that the initial velocity, we were able to work hard last time to show that the initial velocity of F composed beta is E1 of L. So these transversal curves at t equals 0 and at t equals L are the geodesics beta and F composed beta. And hence, if I look at ds d sigma ds at 0, 0, I'm differentiating only in the s direction. So I can put t equals 0 right away. So this is going to be d sigma ds of beta prime, which is 0 because beta is a geodesic. And similarly, d sigma ds at 0L, I'm differentiating only with respect to s twice, so I can put t equals L, and this is going to be ds of f composed beta prime, and that's also 0 because f composed beta is a geodesic. So even though this variation is not proper, these two terms are still 0 for us. Okay, so now I want to keep the picture just because it's so nice. Let's calculate E double prime at 0. So E double prime at 0 is minus the integral from 0 to L of R of E1 of t gamma prime of t gamma prime of t E1 of t dt. And gamma is normalized geodesic, so gamma prime is a unit vector. E1 was also normalized, and it's orthogonal to gamma prime at time 0, and by parallel transport, because these are both parallel along gamma, they're orthogonal everywhere. So E1 of t gamma prime of t is an orthonormal basis of the span of E1 of t gamma prime of t. So that means that this term is exactly the sectional curvature of the plane spanned by these two vectors. And this is where we use that this is positive. We haven't used positive sectional curvature yet, right? Positive sectional curvature. And therefore, I have something strictly positive integrating from 0 to L. I get something positive, there's a negative sign. So E double prime of 0 is negative. Now, why does that give us a contradiction? It's not quite as immediate as it was in the Bonnet-Myers theorem. Because the reason it's not as immediate as it was in Bonnet-Myers is because this variation is not proper, right? So if I look at the other curves in this variation, they're not joining the same two endpoints. In the Bonnet-Myers theorem, once we knew that the second derivative of the energy was negative, we were done because that variation was proper. And so, and that curve that we were using was a minimizing geodesic, right? So that contradicted the fact that it was a global minimum. But now this is not a proper variation. So E double prime of 0 is negative, which means that E prime of S is strictly decreasing on a neighborhood of 0. So there exists a curve alpha in the variation such that the length of alpha, remember the length squared is equal to 2L. This is I can parameterize it by constant speed. This is equal to 2L times the energy. This is strictly length less than 2L times the energy of gamma, which is equal to the length of gamma squared. Okay, so just as we did with the Bonnet-Myers, there is a curve in this variation which has smaller length. So L of alpha is less than L of gamma, but that's not a contradiction yet because alpha doesn't join the same two endpoints. Okay, so alpha of t is going to be sigma of S naught t for some S naught close to 0. And what does that mean? That's exp gamma of t of S naught E1 of t. So what are the initial and final points of this curve? If I put in t equals 0 there, I get x p of s naught e1 of 0, and that's just beta of s0. This is some point q. And if I look at the final point, alpha of L, then this is x f of p of s e1 of L, but that's f composed beta of s naught. Sorry, this is an s naught, and that's f of q. Okay, so q is not equal to p in general, right? But I found a curve alpha whose length is less than gamma, and it joins q to f of q. But there's our contradiction. But gamma joins p to f of p has smallest length among all curves joining q to f of q for any q. That's how we picked it, right? We said that the distance from q to f of q has some strict global positive minimum, and let's take that point, and we get our contradiction. Okay, so there's our contradiction. So f has a fixed point. Okay. Any questions about the proof before we look at the corollaries? All right.
Can you describe the overall strategy? So, because I'm kind of losing it. So you say if there's no, so are you saying if there's no fixed point?
Yeah, so that part we did on Monday. We said if there was no fixed point, then we know the distance from q to f of q is always positive. And because m is compact, that function, distance from q to f of q, and f is continuous and distance is continuous, that has a positive global minimum. And so, and we took a minimizing geodesic joining those 2 points, p and f of p. And then using this issue about the orientation preserving or reversing in this linear algebra lemma, we were able to construct, going through p a geodesic, well, we were able to construct this parallel vector field E1 along gamma, and such that we had a geodesic beta through p with initial velocity E1 at 0, and f of beta we know is a geodesic, and then we know it passes through f of p at time 0. What we had to do last time to work hard was to show that the initial velocity of f composed beta was E1 at L, was the parallel transport here. That's non-trivial, right? That's what we did last time. And then using the positive sectional curvature assumption and the second variation formula, we see that for this variation, we get that the second derivative of the energy is negative, and there we get a contradiction to how we chose p and f of p. Does that make sense?
Yes, that makes sense. I also have like a minor comment on terminology.
Yeah.
So the thing that's being referred to as the energy, if this was classical mechanics, it wouldn't be the energy, it would actually be the action.
It really depends on who you ask, right? So it's a kind of a kinetic energy. It's you're adding up a bunch of speeds with constant mass density.
Well, right, but the kinetic energy of a particle occurs at a point, whereas over a path, the integral of kinetic energy is the action.
This is a continuum. Sure, you can call it the action if you want. I mean, there are other people who call this I'm not the only one who calls this the energy. It's what we're doing there. Yes, yeah.
If you thought it was if it was actually like a continuous string and it was moving, then yes, I think it would be the energy of the string. But if you look at but I kind of think of it as a particle moving through space as a function of time. So really it's the action of that path.
The thing is, in this setting, you can really think of it both ways, because this notion of energy is not unique to geodesic, to curves, right? You can talk about any immersion or any map, smooth map between two Riemannian manifolds, and there's a notion of energy for it, which is some kind of derivative squared, norm squared of a derivative, and integrated over the domain, right? And if you have more than one independent variable, you're not thinking of it as time anymore. So it's not, in this setting, you can think of it as an energy and as an action. But the setting in which it generalizes to in higher dimensions, it's really an energy. And so you could think of this as some kind of string if you want, of vibrating particles or whatever. Okay. All right, so let's look at corollary. Yes. Yeah. What I can't remember. Remind me what you need. Yeah. So that's what the sorry, the question from the audience is. The action is the integral of the kinetic energy, or the kinetic minus the potential, right? And so it's a yeah, potential. You can think of the potential here as being zero, but rather than think of, we're not thinking of this again. It's a sort of a coincidence because this is a one-dimensional object, right? You can think of each point on that curve. Let me see what I'm saying. Mm-hmm. Yeah, it is an energy. Yeah, but what the question was from the audience was that the action from the virtual audience, the action is usually the integral of the energy, right? And he's saying that the speed squared is the sort of pointwise kinetic energy, right? But let's not talk about physics, right? Whatever the terminology, the accepted terminology in math is calling this the energy. Okay, so this is the Sinji theorem. It's a corollary of Weinstein's theorem. It says the following: let Mn G be compact with positive sectional curvature. You notice I've dropped the oriented assumption. So positive sectional curvature, and the theorem has two parts. If M is orientable and N is even, then M is simply connected. And the second part says if N is odd, then in fact M is orientable. Okay, so the blanket assumption for both statements is compact and positive sectional curvature. In part A, we have to assume orientable and N is even, and we conclude simply connected. In part B, we have to assume N is odd and we conclude orientable. So after I give you the proof of this, which will be a corollary of the Weinstein theorem with some facts about topology, we'll see that both of these are required, in the sense that we'll find an example of compact positive sectional curvature where you remove one or the other of these and the conclusion is false. And this is also required. Okay, so there, you can't do better than this. Here's the proof. So first of all, for part A, let's let M tilde be the universal cover of M with the covering metric so the projection, the covering map, is the covering map is a local isometry. Remember, this is how we defined G tilde is defined to be pi star of G. That makes it a local isometry. Moreover, since M is orientable, in part A, we're assuming it's orientable. Since M is orientable, so is the universal cover. And how can you see that? Well, orientable means there exists a nowhere vanishing top form. And then it's easy to see that the pullback, because pi is a local diffeomorphism, the pullback is a nowhere vanishing top form. So this guy is also orientable. So we can choose the orientations so that pi is orientation preserving. Okay. Let's use the fact that M is compact. Since M is compact with positive sectional curvature, there exists some delta positive such that the sectional curvature of M is greater than or equal to delta, which is positive. So this is a shorthand notation, right? I mean that if you take the sectional curvature at some point in the direction of some two plane, you get a real number. So that's a function on the space of all two planes at some point, and that's a continuous function. You can show it in local coordinates if you want. It's a continuous function on a compact set because the space of two planes at a point is a Grassmannian. It's compact, and M is compact. So this has a global lower bound which is positive. And the same, since pi is a local isometry, this estimate here holds for M tilde as well, because local isometries preserve the curvature. Okay, and moreover, the covering metric G tilde is complete. That's something you're proving on assignment 3 for this Friday. From assignment 3, you prove that G tilde is complete. So we can apply Bonnet-Myers to conclude that M tilde is also compact. Right, I have a complete Riemannian metric with positive sectional curvature. Positive sectional curvature implies positive Ricci. Positive sectional implies positive. Anyway, I don't even need this, right? Because, I mean, we already said this when we proved the Bonnet theorem, which was the original simpler version of the Myers theorem. So M tilde is also compact. Now let's let K be a deck transformation of this covering space. Be a deck transformation, also called a covering transformation, depending on where you learned it. Covering transformation. It's a diffeomorphism. It's a diffeomorphism of M tilde with itself, such that K, pi compose K is pi. Okay, that's the definition of a deck transformation. And if I take pullbacks of this, I get K star pi star G is pi star G, which tells me that K star G tilde is G tilde. So K is a local isometry, is an isometry. Isometry, because K is a diffeomorphism and it pulls back G tilde to itself. So what do I have? I have M tilde. Of course, the dimension of M and M tilde is the same, right? So M tilde, G tilde is compact, oriented, even dimensional, with positive sectional curvature. And K K preserves orientation why So let's see. What is a preserve orientation? Yeah, that's right. That's right. Pi preserves. Yeah, that's right. So if you look at thank you. Pi, the determinant of pi lower star is positive, right? And from here, if you take, thank you, pi star composed k star is pi star, and these both preserve orientation, so k preserves orientation, and the dimension is even. So by the Weinstein theorem, k has a fixed point. But then k is the identity, because any deck transformation, this is a topological fact, deck transformation with a fixed point is the identity. It shuffles the fibers around, right? Is the identity. So what do we prove? We prove that any deck transformation is the identity. So there's only one, oh, I didn't want to erase this. There's only one deck transformation. And pi, the cardinality of pi 1 is the number of deck transformations. This is 1. So pi 1 of m is trivial. M is simply connected. That's the proof of part A. Part B, slightly different flavor. In part B, now n was odd. We didn't assume it's orientable. We want to show it's orientable. Okay, so the assumption was mn compact, positive sectional, and n odd. We need to show orientable. So now I have to use some facts about non-orientable manifolds, which you may or may not have seen, and I don't really have time to go over them. So I'm going to tell you what they are, and you can check these on your own. So suppose not, then M is non-orientable. So there exists what's called the oriented double cover. So there's a 2-to-1 covering map, a covering map with 2 sheets where the domain is orientable. So let's let M hat be the oriented double cover of M. So M hat is n-dimensional, orientable, and pi from M hat to M is a 2-sheeted covering map. The way this is defined is if you want to define it locally, you cover M by local charts, okay, and then you add each chart. Basically, each tangent space has 2 possible orientations, right? So you want to look at both of those orientations, so you get 2 charts for here. And the way you construct it, this becomes orientable. So see the exercises in chapter 0 of Do Carmel, if you've never seen this before. And I'm going to state a couple of properties of this oriented double cover in the course of the proof. But it's a local diffeomorphism, so I can certainly pull back the metric here. Let's let G hat be pi star G. Then pi is a local isometry by construction. And since M is compact and pi is 2-sheeted, we get that M hat is compact. I'll leave this for you as an exercise. Basically, whenever you have a covering map with finitely many sheets, and the image is compact, and the domain will be compact. And also, G hat has positive sectional curvature, just like it did in part A, right? Because this is a local isometry. So it'll take positive sectional curvature to positive sectional curvature. Now, let's take a deck transformation of this covering space. So this fact about the number of deck transformations giving the cardinality of pi1, that's only for the universal cover, right? This is not the universal cover I'm doing. This is and sometimes it is, but it doesn't have to be. So let's let K be a deck transformation of this covering space. So again, pi hat composed K is pi hat. And this gives us that K is an isometry. And by this, by here, we get that K is orientation reversing. By the definition of pi hat, which I didn't give you, right? If you look at how this the oriented double cover of a non-orientable manifold works, I mean, here's an example that you should think of. I want to think of the map from S2 to RP2. RP2 is the quotient of S2 over plus or minus 1. Okay, so this is these are both mapping to the same point here, and this is a deck transformation. Sorry, this is an isometry. If K is not the identity, then K is an orientation reversing isometry, because if it's not the identity, there's only two elements in the fiber above the point. It basically, this K is swapping these 2 points, and their image under pi is the same. But these 2 points correspond to the opposite orientations of this, right? That's why K is orientation reversing. I haven't given you an error type proof here because I haven't really told you how to define M hat and pi hat, but you can look that up. So what do we have? We have M hat, G hat is compact, oriented, positive sectional curvature. N is odd, and K is an isometry, which is orientation reversing, which is what we need for the Weinstein theorem. So by the Weinstein theorem, K has a fixed point, but it's a covering map. That means K is the identity, and that's a contradiction, because I have to apply this for not the identity. By the way, this exists. There's always a deck transformation here that's not the identity, because M is not orientable. So there always exists a non-identity K, because M is not orientable. Again, this is some facts about the oriented double cover that I don't really want to get into. So that's the proof of B. Let me remind you exactly what the theorem is we just proved, and show you that all the hypotheses are necessary. So we proved MNG compact, positive sectional, then if MN orientable and N even implies simply connected, and B, we proved N odd implies orientable. Okay, all these hypotheses are necessary. So in the blanket hypothesis is compact and positive sectional curvature. Let me circle these. If we remove either this or this, it fails. And if we remove this, it fails. So all the red hypotheses cannot be relaxed. And we can find examples just by looking at the real projective spaces. So, so here's some facts about real projective space. If n is at least 2, then pi 1 of RP2 is Z mod 2Z. Okay, they're all, none of them are simply connected. RP1 is just S1, which is also not simply connected, but its fundamental group is Z, not Z mod 2Z. RP even is non-orientable. RP odd is orientable. Again, RP1 is S1. RP3 is actually diffeomorphic to SO3, the Lie group SO3. And if you take the 2-to-1 projection from Sn to Rpn, which this gives me the equivalence class of plus or minus p, right? This is a quotient of Sn by the antipodal map. This is a submersion. It's a local diffeomorphism. Local diffeomorphism. And you can define a metric. In general, if you have a local diffeomorphism, you can pull back a metric from the codomain to the domain, right? Here we have a metric on the domain, but you can show, because of the nature of this map, that it's the quotient by the antipodal map, one can show that the round metric on Sn descends to a quotient metric on Rpn, which also has constant positive sectional curvature. When we talked about constant sectional curvature spaces, we proved that if you had positive constant sectional curvature and at least 2, it's isometric to Sn with the round metric, right? And this guy is a quotient by the antipodal map. The antipodal map is an isometry, and it acts properly discontinuously. So that's the condition you need for a metric to descend to a quotient, right? And then the way you put this metric on Rpn, it makes pi a local isometry, and so this makes pi a local isometry. Okay, so this is the standard metric on Rpn. Standard metric on Rpn. And now let's see that these give us examples, right? So if we look at Rp2, this is 2-dimensional and non-orientable and not simply connected. Okay, so hence orientable is necessary in A, right? Of course, this is compact. Rpn is compact. It's a quotient of the sphere. So it's compact. It has a positive sectional curvature metric. So these two guys are satisfied. Rp2 is in the even dimensional case, but it's not orientable. And the conclusion is it's not simply, like, the conclusion doesn't hold, right? So we needed orientability in part A. And n is odd is necessary in B with the same example. Necessary in B because if it wasn't, so B says that if you have compact positive sectional curvature, it has to be orientable. But this is a compact positive sectional curvature which is not orientable, but the difference is that it's not odd dimensional, it's even dimensional. So RP2 shows you that this is necessary and also that this is necessary. And then RP3 is orientable and not simply connected. So N even is necessary in A. The only thing that RP3 has that doesn't fit here is that it's odd dimensional. So this is also required. Okay. Any questions about any of that? Okay. So, break. We finished chapter 9. We did basically everything in chapter 9. We're moving on to chapter 10, which is the Rauch comparison theorem. We're only going to do half of chapter 10, the first two sections. We're going to prove the index lemma and the Rauch comparison theorem, which I'll start to talk about now. In the third and fourth sections of chapter 10, the author generalizes the Rauch comparison theorem to a more general setting where you're looking at submanifolds and applying it to isometric immersions. But that's the material from chapter 6 that I skipped, right? So because we skipped chapter 6, we have to skip the second half of chapter 10. But then I think we'll do all of 11 and 12 before the term ends, and we'll see how much time we have to do some of 13. Okay, so what is the Rauch comparison theorem? Let's give a sort of a informal introduction and remind ourselves in the process about a result from a long time ago. So recall from chapter 5 on Jacobi fields, we had the following result, which was basically telling us in what precise sense Jacobi fields are measuring the spreading of geodesics. Okay, so if curvature tells you how much geodesics are spreading out. If gamma is a geodesic, let's say normalized, and J is a Jacobi field along gamma with J of 0 is 0 and J prime of 0 has length 1 and J prime of 0 is orthogonal to gamma prime of 0. If we had these three properties, then we proved that the norm of J of t is t times k over 6 t cubed plus some remainder, which is little o of t cubed. That means that the limit as t goes to 0 of the remainder divided by t cubed is 0. And k is the sectional curvature of the plane spanned by gamma prime of 0 and j prime of 0. Those are both unit vectors. Gamma prime of 0 is a unit vector because it's a normalized geodesic. J prime of 0 is a unit vector here, and they're orthogonal, right? So they span a two-plane, and this has some sectional curvature. So the picture was if this is gamma, and we have some Jacobi field, this is J prime at 0. and this is gamma prime at 0. This this is a two-plane which has some sectional curvature, and we argued when we did this in chapter 5 why this is somehow telling you that the curvature controls how fast geodesics are spreading apart or converging close to each other. Okay, so we're not going to go back to that notion of the spreading of geodesics, but if you look at this fact, what does this say? This says that if it goes to 0 as t goes to 0, right? So for t sufficiently small, it's certainly going to be less than 1 in absolute value. So if t is sufficiently small, then the remainder is less than or equal to t cubed. Okay, because the remainder over t cubed is less than 1. So now suppose that m tilde g tilde is another Riemannian manifold, which doesn't even have to be of the same dimension, not necessarily the same dimension. This is really the power of the Rauch comparison theorem. A lot of the things we did in the last few weeks, we were comparing whenever we had two Riemannian manifolds, they had the same dimension. And suppose gamma tilde is a geodesic. Right, this, I took the same L there, but you can just shrink these geodesics to make sure they're defined on the same closed bounded interval. It's okay. And suppose J tilde is a Jacobi field along gamma tilde with the same properties. J tilde of 0 is 0. J tilde prime at 0 has length 1. And J tilde prime at 0 is orthogonal to gamma tilde prime at 0. Okay, so then I can apply the same result there. Then J tilde t is equal to t minus capital K tilde t cubed over 6 plus little o of t cubed, where K tilde is the sectional curvature span of the span gamma tilde prime of 0 and J tilde prime of 0. It's exactly the same statement again. So again, for t sufficiently small, this thing will be less than t cubed. This is less than t cubed for t small. Therefore, so if the sectional curvature of this two plane, this is what I called K tilde in here. If this is greater than or equal to K, which is K of gamma prime 0, J prime 0, then that means that if K tilde is bigger than K, that means that minus K tilde is less than or equal to minus K. So J tilde T is less than or equal to J of T for T sufficiently small. Yeah. Yeah. What? Yeah, this is the remainder. Sorry, I shouldn't have done that. That's exactly why I didn't call it R over there, because I didn't want to get it confused with curvature. Okay, so the point is, for this statement that we're talking about, this power series, Taylor series expansion of the norm of the Jacobi field in terms of the sectional curvature, is independent of dimension. And therefore, if you have two Riemannian manifolds and you have two Jacobi fields that vanish at the origin at time 0 and whose first derivative is normalized to be length 1 and it's orthogonal, it's a normal Jacobi field, then if you can compare the sectional curvatures, you can compare the lengths of the Jacobi fields. Okay, Now, it's not clear why this is useful, right? Except hopefully you've been convinced over the last few weeks that Jacobi fields tell you a lot of useful information about the geometry. So the whole point of the Rauch comparison theorem is to take this away. Right? We want this to hold for all t. So the Rauch comparison theorem is a generalization of this argument so that k tilde greater than or equal to k everywhere implies j tilde t less than or equal to j of t everywhere, not just small t. But there's some technical hypotheses we need to put in there to make it true, which I'm not telling you yet. We need some technical hypotheses about conjugate points, about not having conjugate points. Okay, in fact, you'll see them in a few minutes, because what I want to do for the rest of today, and I think I can do it, is I'm not going to tell you what the Rauch comparison theorem is yet. We'll do that on Monday. But we need a preliminary lemma called the index lemma to prove the Rauch comparison theorem. And we're also going to need the index lemma for the Morse index theorem in chapter 11. So this has multiple uses. And the index lemma basically tells you something about Jacobi fields and curvature. And there's some technical hypothesis about conjugate points. And the index lemma is something we could have done at the end of chapter 5, because it only required the material from chapter 5. The reason that the author doesn't do it in chapter 5 is he doesn't need it until now. And also it would look very strange showing up there, because the index lemma involves the index form, which is the thing that shows up in the second variation formula for the energy. Okay, so if you haven't talked about the second variation of energy to derive this expression, it's very mysterious why that thing is of interest. Okay, so for the rest of today, as I said, I will state the precise form of Rauch comparison on Monday. For the rest of today, we're gonna try to prove the index lemma. What I need, before I can do that, I need the following trivial lemma. Let H be a smooth function on closed 0, 1 with H of 0 equals 0. Then there exists a smooth function phi with H of t is t times phi of t for all t, and phi of 0 is H prime of 0. I'm going to have to use this twice in the proof of the index lemma. So why is this true? This is trivial. Let's define phi of t to be the integral from 0 to 1 H prime of t u du. Okay, if I do this, this is certainly smooth because H is smooth and I'm taking integral. Then t times phi of t, I can bring the t inside. And then if I let s equals t times u, this is going to be 0 to t h prime of s ds, and that's h of t, because h of 0 is 0. Right? That's why that term drops out. And just from this, if you just differentiate this and set t equal to 0, you get this. So I'm going to use this a couple times. Now, here is, well, let's recall what the index form is. So let gamma be a geodesic. We're working on one Riemannian manifold. Let V be a piecewise smooth vector field along gamma. And then for any T naught in 0 to A, in fact, I can put 0 as well, it's not important. Recall we had defined I T naught of VV is the integral from 0 to T naught of V prime, inner product V prime minus R of V gamma prime V dt. Okay, so this is exactly when T naught equals A, this is the part of the second variation formula. This is the integral part of the second variation formula for energy. Of the variation vector field V on gamma restricted to 0 T naught. Okay, so V is a piecewise smooth vector field along gamma. I can restrict it to 0 T naught. Gamma is still a geodesic on 0 T naught. If you do the second variation formula on that interval, 0 to T naught, this is the term that shows up, plus a bunch of other terms that go away when you have a proper variation. Okay. So this is the index form. This is called the index form of the geodesic gamma restricted to 0 T naught. So it's a symmetric bilinear form, or equivalently a quadratic form, on the space of piecewise smooth vector fields along this geodesic. So it's a quadratic form on the space of piecewise smooth vector fields along gamma restricted to 0 to T naught. Okay, so let me state the index lemma. It's basically telling you something about this quadratic form, which is the following. And it's going to be an easy proof, just a computation. I mean, it's long, but it's just a computation. I think I can do it all. So this is the index lemma. So we have a geodesic as before. We have to make an assumption. Suppose gamma of T is not conjugate to gamma of 0 for all T bigger than 0 up to A. Remember, what does it mean to be conjugate? It means there exists a non-trivial Jacobi field which vanishes at 0 and at T. Let J be a Jacobi field along gamma with J inner product gamma prime is 0. So this is a normal Jacobi field. And let V be a piecewise smooth vector field along gamma with V gamma prime is 0 for all T. Okay, so both J and V are orthogonal to the velocity of gamma everywhere. Suppose that J and V vanish at the initial time, and that there's some positive time where they agree for some T naught strictly positive up to A. These need not be zero. They just agree. Okay. In fact, if they were zero, then J would be zero. So in fact, if J of T naught is zero, that implies that J is identically zero on 0 T naught because there's no conjugate points. So if I had a Jacobi field which vanishes at time 0 and at some positive time T naught, that's exactly saying that gamma of T naught is a conjugate point. So we're assuming they both vanish at time 0 and that they're equal at some positive time. Then the index form up to T naught of JJ is less than or equal to the index form up to T naught of VV, with equality if and only if J equals V on 0 to T naught. Obviously, if J equals V on 0 to T naught, we have equality here. This says that the Jacobi field, if you have no conjugate points, a Jacobi field assumes the global minimum of the index form among all piecewise smooth vector fields. And the only other point, I mean, the only way to get that same minimum value is with J itself. There is no other way to get it. Okay, I have 13 minutes. I might have to, again, leave a proof in the middle, which is unfortunate, but let's see. Maybe I can do it. So let script J be the space of Jacobi fields along gamma with J of 0 equals 0 and J prime of 0 orthogonal to gamma prime of 0. So we proved earlier that this implies, in fact, is equivalent to J prime gamma prime is 0 for all T. When we finished chapter 5, we went through some properties of Jacobi fields, and this is one of them, right? That if it's initially 0, then its initial velocity is orthogonal to its initial covariant derivative is orthogonal to the initial velocity of gamma, if and only if it's true at all for all times T. And this space J is a vector space of dimension n-1. Right? This came from the properties of Jacobi fields. Because they're vanishing at time 0, we only have half of them, n-dimensional space. And because they're orthogonal to this one, we lose one more dimension. So let's let J1 up to Jn-1 be a basis of script J. We're going to use this to write both J and V. But of course, V is not a Jacobi field, right? So we have to see in what sense we can express V in terms of these J's. So we can write J as the sum over K, alpha K, JK. This is from 1 to n-1, where the alpha K's are constants, right? Because J belongs to this script J, and these are a basis. And since there are no conjugate points along gamma, by an earlier result, again, this is at the end of chapter 5, we stated some properties of Jacobi fields. We know that J1 of T up to Jn-1 of T, sorry, that's right, is a basis of T gamma Tm for all T in open 0 up to A. Okay, this is exactly the result we proved. We said if you have a basis for the space script J, and there's no conjugate points, then for every positive time T, this gives you a basis for this tangent, basis of the orthogonal complement of gamma prime of 0, gamma prime of T in T gamma of T. These guys are all orthogonal to gamma prime of T, and they're a linearly independent set. So why do we have to avoid T equals 0? Because at T equals 0, these guys are all 0. Right? These are all in script J. So if T is not equal to 0, we can write V is piecewise smooth. We can write V in terms of some functions times the JKs, because for T positive, that's a basis at every time T, and therefore I get these coefficients which depend on T. So Fk is defined on open 0 up to closed A, and it's piecewise smooth. Piecewise smooth because V is piecewise smooth. The J's are smooth, so any jumps have to occur in the F's. Okay, so the first claim, we can extend the FKs smoothly to all of 0A. They extend smoothly to T equals 0. And let's see why that's true. Here's where I'm gonna use that calculus fact that I erased. So since JK of 0 equals 0, by the lemma, really suitably adapted. I did this lemma for real valued functions, but as long as I take values in a fixed finite dimensional real vector space or any real vector space, the lemma still works. So since JK equals 0, we can write JK of T is T times AK of T, where AK is smooth vector field along gamma, and AK at 0 is JK prime at 0. This is exactly that thing. This was H and this was phi. Okay, but J1 prime at 0 up to Jn prime, Jn minus 1 prime at 0 are linearly independent. And that's because J1 up to Jn minus 1 is a basis of script J. Remember, script J were those Jacobi fields which vanish at the origin. So the other condition you need from the ODE theorem is the first derivative at time 0. And since these are linearly dependent, that means their first derivatives at time 0 are linearly independent. But that's this. So AK A1 at 0 up to AN minus 1 at 0 are linearly independent. But it's also true, unfortunately I have to erase the lemma, it's also true at other times T, because at positive times, the A's are just a positive multiple of the J's, and those are linearly independent. So also for T positive, A1 of T up to AN minus 1 of T are linearly independent. Okay, so hence, A1 of T up to AN minus 1 of T is a basis of T gamma of T M for all T, even at 0. Okay, so we can write VK at T, sorry, not K, V at T is the sum from K equals 1 up to N minus 1 of some GK of T, AK of T, where GK are piecewise smooth. And now we can do this for all times, right? Because the A's are good for all times. So we have these GKs, they're piecewise, the A's are smooth because the A's were given from that lemma. And moreover, GK of 0 equals 0 for all K, for all K, because V of 0 is 0. Right, that was one of our hypotheses in the lemma, which I've now erased. So by that calculus lemma again, we can write GK is T times HK of T, where HK is piecewise smooth on 0A. Really, the lemma I did was from 0 to 1, right? That 1 was meaningless. It could be anything. And because these guys are all piecewise smooth and I have a finite number of them, I can just restrict that calculus lemma to the interval on which they're all smooth, right? Make it small enough so they're all smooth. So then what do we have? We have that V is the sum over K GK AK, which is the sum over K T HK AK, which is the sum over K of FK JK. Okay, so this and this is for all T in 0A. And this in fact, this is okay. So what have I done here? No, sorry. This is true. And it's also, V is also equal to this, right? On away from A. Okay, so therefore, and this thing is JK. Sorry. This is equal to the sum over K HK JK, right? Because T times AK is JK. So what we've shown is that the FKs extend smoothly to T equals 0. So FK equals HK on 0 to A, and HK is smooth, piecewise smooth on 0A. So FK extends smoothly to T equals 0. Right, that's the end of claim number 1. So we've shown that there exists FK from 0 to A to M piecewise, sorry, to M to, what am I saying? To R. What have I been writing? These are real values. Nobody's catching me. This doesn't make any sense, right? They're real valued. They're the coefficients in a real vector space. So there exists these guys, piecewise smooth, on the whole 0 to A, such that V of T is the sum from K equals 1 up to N minus 1 Fk of T Jk of T. And we also know that J is the sum from K equals 1 up to N minus 1 alpha K Jk of T, where these are real numbers. Okay, I might as well stop here because I only have 2 minutes. On Monday, I'll restate the index lemma, and I'll say this is where we got to, right? So I don't have to do all this calculus stuff again. We're more than halfway through the proof. The next thing is just a tedious computation that'll take 5 minutes, and then from there, so there's some tedious computation, and then we have to use some facts again about Jacobi fields. And the assumption of no conjugate point. So let's stop here on Monday. I'll restate the index lemma, and I'll remind you that we've gotten to here. Okay, and we'll continue from there.